Okay, so today's lecture is about the optical mode in semiconductor cavity. So, if you ever take the class about electromagnetism, which talked about waveguide, it's actually the content is pretty the same. So that will make this one an easy one. But in this class or this textbook, focus on calculating some real numbers. So beside the field, we were doing some real approaches about how to calculate the optical mode. Yeah, with an easier way. Considering you are a scientist 40 years ago, so you don't have so the good computer and simulation tool. How do they do? How do they do that? All right. So let's consider a pretty common waveguide structure with 3 layers. Then the layers at outer side is called cladding layer. And the one in the inner side is called the core layer or guiding layer. And the refract index of the core layer must be higher than the cladding layers. Whether the cladding layer has the same refract index, not for sure, but usually the cladding layer at the top and at the bottom has the same refract index. N3 is equal to N1 and less than N2. So if we have a light, a semiconductor layer looks like this, and the light is coming in the core layer with a relatively large incident angle. As long as the incident angle is large enough, it will cause the total internal reflection back and forth. Then, if the light after 2 total internal reflection, and if they are constructively interfere with each other, then there's an optical mode for that. So you can consider the light bouncing back and forth as the real wave vector with a refract index of N2. However, while you're bouncing back and forth, you have the component parallel to the waveguide. We call the projection to be K0 NEFF. NEFF means the light effective refract index if the light is considered here as a plane wave, not a bouncing wave. Yeah. So you have an effective index to treat the mode as plane wave. And similarly, we have a light that projecting along the surface normal called Kx. Let's say that the AP is going along the x direction, and the light is propagating along the y direction. Alright. So, because we already know that the light will be interfering with each other, then it will cause something like wave bracket about that way. So we said that this form is called the U of xy. That means this wavefront is in the xy plane, the function of x and y, and it effectively propagating along the direction. So we write it down the electric field like this. EI is the field of the polarization. E0 is the magnitude. UFXY is the light amplitude profile in the xy projection. And because it looks like propagating along the direction. So the exponential term turns to the I beta d minus omega t, which is in the form of plane wave. And the beta is normalized to its wave vector in the vacuum. So the difference is the NEFF. According to this plot, we know that the NEF is definitely smaller than N2. But it also needs to larger than N1 and N3. It is a value between the high refract index and the low refract index. About such mode, the direction of polarization matters. If the polarization is parallel, the electric field is parallel to the interface, then it's called the transverse electric field mode. If you form the mode and there's an electric field, it's polarizing with the field, like the field is getting out of this plane, then it's T mode. In the same way, if it is the magnetic field oscillating out of this plane, then it's called the TM mode, transverse magnetic field. Alright, so to solve the mode, we need to solve its Maxwell equation, or the side product of the Maxwell equation. We call it Helmholtz equation. The Helmholtz equation is the electric field doing the Laplacian, and it's equal to its permittivity and the permeability. The two words sound pretty the permittivity or permittivity. Yeah, and the double second time derivative of the electric field. This is the Helmholtz equation. This is the result of Maxwell equation into one. Alright? So the mu is usually the magnetic permittivity is usually the same with the vacuum one. So this is not the problem we want to deal with now. The problem is that the material, the dielectric function, has its real part and its imaginary part. So the actual zero is the dielectric constant in vacuum. But under some wavelengths, it could be absorbing, or you have a very strong interaction with that. So it gives the real part of the electric field, which is more relevant to the polarizability of the material. This is taught in other classes, so I don't spend too much time on that. You can just think it is something relevant to the refractive index of the material. And the imaginary part is more relevant to the optical panel loss. Yeah. So the dielectric function is a complex value. It is usable to evaluate the material property with one word. Okay. So to solve the wave equation, or to solve the optical field in such slab waveguide, we just directly insert the whole electric field, the whole term, into this equation. So if we do a Laplacian, that means you are extracting the deriving it twice. So what it will drop a double beta. You will the I beta and I beta, we will give it a beta twice. So it should give a minus beta squared. And the minus beta squared is minus k0 squared times n e and m squared. So this is what it comes out in the left hand side. And in the right hand side, what happens here? You will give you double omega. It will drop minus omega twice. So it will give you a omega squared. Then you can eliminate the common term at the both sides. The final result is du over dx squared. Because you're doing the Laplacian, so you are gonna do the differential along the xy report. So the this gives you the minus beta squared, and this gives you the d over du squared dx squared. And the things we are only considering in the one dimension, so this term is omitted. So that gives you the n du over dx squared, second derivative, plus n squared, because n is the relation here. So you already obtain n from its this term. So you got your term from here. So finally the wave equation reduced to the term like this: du over dx squared plus nx squared. Nx squared means the refractive index of such a material, minus effective refractive index square, k square ux. Okay. So if we see this is the drawing of the refract index profile. N2 is higher, it's in the middle, and its distance is d. And the N1, and let's assume a symmetric case first. N1 is N equal to N3, and it is lower than N1. To obtain, and for obvious reason, the NEFF must be less than N2. Okay? So let's consider the equation in the central region. Because when N is N2, so N plus square minus NEFF square is a positive value. So what happens when this will hold? It only happens when the term is writing as A exponential IKX. So to be more precise, it should be a form like in the core region. So you see this is in the form of sinusoidal wave or plane wave in the center. If NEFF is lower than N1, let's just consider an imaginary case. That means the wave function outside the cladding layer is also sinusoidal wave. Then this function is not bounded. It's not bounded. It can be extended to infinity direction. So it doesn't form a waveguide mode. So if you want to form a optical mode within a limited space, it's just like a bounded state over the quantum wave electron. The NEF is much larger than N1. So if the second case, if the N1 is smaller than NEF, this is a minus value. And its wave function has to be written in exponential, no I anymore, plus or gamma minus gamma x. Since the wave is bounded, you cannot go to infinity at the long way. So when the x is larger than 0, let's call it phi 3. It has to be c exponential minus gamma x. If it is plus, then it will propagate to the infinity. It doesn't make sense. And the phi 1 is c is the d exponential plus gamma x. Alright. Okay. So then we need to solve the boundary condition to see what it really looks like. Alright. So this is the case. U1 is the b exponential gamma x, and for the symmetric solution, that means the wave function is symmetric to each other. Then we can directly assume a reasonable assume U2 is a cosine kx squared, and the U3 is b exponential minus x because it is symmetric. And the kx, according to the wave equation, is n2 squared minus NEFF squared. Take a square root times k0. Similarly, gamma is the NEFF minus N1 squared because NEFF is be larger than N1. So it is NEFF squared minus N1 squared. Also take a square root. Then times the wave vector in the vacuum. Okay, so we see if we take the square of k and the gamma, what do we have? The NEFF will be eliminated. So there will be no unknown value. So we know that the k squared plus gamma squared should be the n2 square minus n1 square times k0 square. Okay. Because this number is important, we give it an important name. But in this case, this is not a uniless value. So we define a normalized frequency, we call it V. V is we times d squared, the width of the circular guide at both sides. So k squared plus gamma squared times d squared, it becomes a uniless value. And we call this uniless value to be v squared. This will help us to simplify the calculation. Okay, so now we have the notation here, so we need to solve the boundary condition at the interface. The first boundary condition is that the optical field need to be continuous at its boundary. This is for sure. So we put it in half of d at both sides. So a cosine kx times half of d is equal to b exponential. We're talking this interface here. So make a drawing. I think the drawing is already in the next page. I don't need to go here. It's equal to b exponential minus gamma d divided by 2. Second, the derivative also need to be continuous. This has also a physical meaning anyway. So cosine divide take a differential, you will drop kx, and the cosine become minus sine. And the gamma also drop a minus gamma, so we can eliminate gamma, the minus at both sides. So we can like akx sine kx 2 over d equal to b gamma exponential minus gamma times d over d. Alright. Then we divide this equation by this equation. So the exponential term is eliminated. So it becomes kx sine divided by cosine, kx tangent. Kx times half of d should be equal to gamma. So tangent kxd divided by gamma should be gamma over kx. Then we smartly times d at both sides. Alright. And we be even smarter to take a square, then take a square root. So with a very strong sense to do such mathematical work. Alright, so it becomes tangent half of kd is equal to square root k d gamma d squared over k d squared. And we want to make the equation only one unknown. Okay, luckily we know that kx squared times gamma d squared is equal to b. Alright, so the gamma d squared becomes b squared minus k squared over k squared. Alright, so then we can finally let x be kd. So it becomes a uniless boundary condition like this. Tangent half of x is equal to square root b squared minus x squared divided by x squared. So this is the boundary condition for a symmetric waveguide. Similarly, you can do the same thing with the asymmetric solution. The asymmetric case, just assume the first. The U2 is A sin kx, so this is the symmetric function. And because we already know it's a symmetric function, so we can write down with confidence that the gamma 1 is minus B gamma x. So if you put a minus x in, it will give you the number like here. So it's an odd function. Then we do the same procedure again. You will get the minus cotangent kx to b is equal to also b squared minus kb squared divided by kx squared. And the minus cotangent, it can be further transformed into tangent kb over 2 divided by half of pi. So, okay, so we also solved this equation by the left hand side and the right hand side. So let's draw we smartly make the right hand side in the same form. So we can imagine what the right hand side is. The right hand side when x is equal to very close to 0, and the since b is not 0, it's a value approaching infinity. Okay, so that's the one end. And the second end is if x is increasing, it cannot be larger than b. If x is larger than b, it cannot be calculated. So it will eventually goes from infinity and decrease until b. Okay, so right hand side is a curve like the black curve. And the left hand side it could be either tangent or tangent minus half of pi. So when the waveguide have a solution, that's only when these two lines intersect. Alright. So, for example, if your b is more less than, so the radius is already normalized with pi. So if your b is small, for example, your index difference is small, or your distance, the waveguide thickness is big, you might get a pretty small b. But anyway, you will get one optical mode at least. You definitely get one optical mode because it's a finite value here, and it will go from infinity to 0. Definitely get a point here. So you will at least one fundamental mode. If your b is high, if your b has high, for example, your b might be like 1.5 pi. Then in this case, you at least get 2 points. So if the refractive difference is large, or the waveguide thickness is wide, so it's the overall value that determines how many optical modes should exist in such slab waveguide. Alright. So this is a case of the n is equal to 0 case. It's a fundamental mode. And because the kx is in the minimal value. Okay, let's return to this page. If the kx is in its minimal value, but the k2, the n2 is a constant, that means you have the highest effective mass for such waveguide. Alright. So the fundamental mode is the waveguide mode with the highest effective index among them. And for a symmetric waveguide, there will be at least one fundamental mode for the waveguide. Alright, let's take a short break. I will return with the 210.